Okay, we've arrived at an important point for us. This is kind of a milestone because you've learned enough reactions now that you can start stringing them together in meaningful ways. And this is really a lot of what organic chemists do in their day to day is think about ways to make new molecules. Um, so we call this process organic synthesis. Um, And the idea is you might have a target molecule that you want to produce, but you need to find a way to produce that molecule from chemicals that are available to you. So you've got to be able to go to a chemical supply company, order certain chemicals, and then put them together in a way to make your new chemical that wasn't previously available. Um, that sequence ends up breaking down as diagrammed on this page. So if you look at the bottom of the page, you can see this molecule, cetirizine, also known by the brand name Zyrtec. Some of you may take this as an antihistamine um, that people use to tamp down their allergies. So some of you may be very familiar with it. Um, so let's say I wanted to make Zyrtec, but I need to start with things that are available on the market. So this is the original synthesis of Zyrtec. This is how it was produced. So you're starting with this molecule here, um, which is available, and we're trying to get all the way to that target. Um, a number of the steps in this sequence you have already seen. Um, So this first one you haven't seen before. That would be in an upcoming module, potentially. But this is a reaction that uses NABH4 to reduce a ketone to an alcohol. Notice we start with a ketone here, and we end with a secondary alcohol. That's a reduction. You did learn back in Module 14 about reductions. So this is a reduction because we're going from oxidation level 2 to oxidation level 1. Um, this second step is a step you've seen before. That's where we're using thionyl chloride and pyridine to replace an alcohol with an alkyl chloride. Okay, so this you definitely saw this last module in Module 23. And then the next reaction actually is an SN2 reaction. You have seen that before. You haven't necessarily seen it with this nucleophile, but you have seen this kind of reaction before. This would be just a regular old SN2 followed by deprotonation by pyridine. To yield this next intermediate in the sequence. Um, you might recognize NaH as a base that's going to deprotonate our alcohol. To make life easy, I'm going to abbreviate the rest of this molecule as R. So when I deprotonate, I will have R with now an alkoxide at the end of this chain. Um, and and then I'm adding another alkyl chloride. So this is just going to do an SN2 reaction. Again, a reaction that you've seen. And that gives me this next intermediate. This last step, this is a reaction you would learn much later in the course. That turns that amide on the far right into a carboxylic acid. Um, and that's the sequence. So that's the kind of process that we want to go through. I want you to start to develop your skill of thinking about how to put reactions together in multiple steps in order to come up with a sequence like this. Okay. So the first thing you're going to want to do before you can really do synthesis is organize your thoughts around reactions that you know. So I've included a bunch of pages here um, where you can organize your thoughts around reactions that you know, because you need to learn how those reactions work, and you need to know what functional groups you can turn into what other functional groups before you can do this process. Um, so I'm not going to go through and fill in this whole chart, but I'll give you an example of how to fill it in. But for every reaction, there's really 4 categories of information you want to know about it. You want to know the starting material, you want to know the reagents that are used, you want to know the products, and you want to know something about how it happens, or what the stereochemical outcome is, what the regiochemical outcome is. Do things go to the more substituted carbon? Do they go to the less substituted carbon, etc.? And making yourself a table like this is a good way to start to organize that information. It also gives you a good way to quiz yourself about that information later on. So you can cover up 1 column at a time or 2 columns at a time and quiz yourself on what goes in between. It's a good way to force your brain to practice that recall, which you would need to know for tests. This ends up being usually an important part of tests in an intro organic chem class. So let me show you what I mean about filling in this chart. We learned a lot of reactions of alkenes. So let's start with a reaction of alkenes. I know I can react an alkene with HX, where X is Cl or Br or I. And my product was an alkyl halide. I may want to include an example. So if I start with this alkene and I react with HCl, I would make an alkyl halide. The chlorine would go to the more substituted carbon of the double bond. Hydrogen goes to the less substituted carbon. So for notes about this, I might say it goes through a carbocation. I would say Cl or X goes to the more substituted carbon. And that would be one of my entries. Another reaction of alkenes that we learned was the reaction with H2O with an acid catalyst. That made an alcohol. Again, for an example, I could use this alkene, and if I did this process, I would make the alcohol on the more substituted carbon. This has really the same notes as the previous one. It goes through a carbocation. The OH goes to the more substituted carbon. Another way to say that would be to say this is a Markovnikov addition, if you remember that terminology. So I would fill in this chart for every reaction that I've learned. I know that's a lot, but guess what? Organic chemistry is a lot, and it's going to be challenging when you take it in the future. So learning these techniques for storing all that information and studying it is going to be helpful. Just to give you an example, we also learned that with an alkene, we did some 2-step sequences with alkenes. For instance, we did step 1, H mercury acetate and water. Step 2, NaBH4. When we did that, again, we made an alcohol. It also went to the more substituted carbon. Now you may remember the difference in this case was there was no carbocation. So we didn't have to worry about rearrangement. So that's an example of a two-step sequence that I would include sort of as a single entry in this chart. Um, and then one other quirk is that we've learned some reactions that had two organic molecules involved. So for instance, I could take an alkene and react with an alcohol and an acid catalyst. So for instance, I could do this with, say, ethanol and H+, um, and that's going to make an ether. That goes through a carbocation, and the OR group goes to the more substituted carbon. But because there I had my alkene listed as a starting material and the alcohol listed as a reagent, I also want to enter this a second time, but reverse those two, because there may be scenarios where the thing I'm starting with is the alcohol. And I want to remember that I can react that with an alkene and an acid catalyst to make an ether. So some of these reactions I would actually list twice. I would have one entry for this reaction, starting with the alkene, listing the alcohol as my reagent. I could also start this with the alcohol and have an alkene and H plus as my reagents. So this is a second entry for the same reaction, but it'll be helpful to me because now I can recognize when I start with an alkene, I can do this reaction, or when I start with an alcohol, I could do this reaction. So it might look a little different in this case, but the result is going to be the same. I can write the same notes, so I'm just going to copy and paste them. So if you look through all your notes for all the reactions you've seen, you should be able to fill in a lot of rows of this chart. So I left you a lot of rows here. I'll give you one more example before I quit filling it in and just leave the rest to you. For the SN2 reaction, seems like just one reaction, but because we used so many different nucleophiles, the SN2 reaction would end up being many entries. So you can start with an alkyl halide. And then for reagents, we saw lots of different nucleophiles. So for instance, I could add NaCN, and that would make a nitrile. That's an SN2 mechanism. You might make a note about inverting stereochemistry if it's applicable. And then you might, in your next entry, start with an alkyl halide, and let's add SH minus as my nucleophile. That's going to make a thiol as the product. So you could end up with 6 or 7 different entries, maybe even more, for the SN2 reaction alone, because it allows you to make so many different functional groups. So as you're making this chart, bear that in mind. If you want to check with me at any point and say, hey, how's my chart look? I am more than happy to look at it for you. But this is a useful way to start to organize your thoughts around reactions and get to know the reactions well enough that you'll be able to recall them later, because you really need to be able to have these in working memory in order to put them together. The first step is learning how the reactions work. and then you put them together into combinations that do what you want. I often make the analogy, this is like playing chess. You need to first learn how the pieces move before you can play chess. Just because you know how the pieces move doesn't mean you can play chess yet, or doesn't mean you can play chess well. Um, that still takes practice, but without knowing how the pieces move, you're helpless. So this is just learning how the pieces move, and then practice with synthesis problems is really how you learn to play the game of chess. Um, so keep that in mind. It is a lot of work, but no one said organic chemistry is really easy, and that's why I took it. Um, so once you know your reactions well, then you're going to start approaching synthesis problems. And synthesis problems tend to look like this. You have a desired product and you have a starting material. And you're told, okay, provide a complete synthesis of the following desired product from the indicated starting material. You may use any inorganic or organic reagents you wish, but all carbons from the starting material must end up in the product. You do not need to show any mechanisms. So this is really just knowing the outcomes, not necessarily worrying about the curved arrow mechanisms for each step. So I want you to follow a specific process when you approach these problems. First of all, take a deep breath. I used to work with a professor who would say, step one, don't panic, but that's starting with a negative. I like to start with a positive. So take a deep breath, okay? Even when you're looking at unfamiliar molecules, it might seem overwhelming at first. Take a breath, reassure yourself. Next, I want you to identify functional groups. In the starting material and the product. All right. Looking back at the synthesis I used to introduce this, if you were given this page and you were just shown the beginning and the end, wow, that looks really overwhelming. There are a lot of different things going on. But what you can do by identifying functional groups is those become the familiar pieces of molecules that can help you relax. Um, most of us have had the experience where you walk into a party and you don't immediately know people and you might feel overwhelmed right away. But then you find a friend, you find two friends, and you start to feel more comfortable. Finding the functional groups is really like finding your friends. So, for instance, in this example, I would start by saying, okay, my starting material is an alkene, and my product is an ether. All right, so I have an alkene and I have an ether. Great. Step 3 is going to be to count and number your carbons. And then two key things. You're going to look for new carbon-carbon bonds. Those are a little tough for us to form right now, but as you move on in organic chemistry, those become key steps in syntheses. And also try to match up the carbons in the starting material with specific carbons in the product. So for this example at the bottom of the page, I would say, okay, I have 1, 2, 3, 4 carbons here. And I have 1, 2, 3, 4 carbons here, and 1, 2, 3, 4 carbons here. So it seems like I can take the starting material, and it could be either the 4 carbons on the left, or it could be the 4 carbons on the right. I could also number these in the product as 5, 6, 7, 8 on the right. But I'm not sure to begin with which ones are going to be which. So if I wanted to, I could say 5, 6, 7, 8, or I could say 1, 2, 3, 4. And then there's the last piece, and this is the piece that people find really challenging at first, and that is to work backward from the product. This is often known as retrosynthetic analysis. Um, organic chemists tend to use a wide arrow that looks like this um, as what we call our retrosynthetic arrow. Um, anytime we are starting with a product and thinking backwards to a potential precursor molecule. Um, so when you look at answers for these, you'll often see me use those. Um, that's what they mean. It's just a sign that I was working backwards when I thought that way. Okay, so I look at the product and I see the product is an ether. And to work backwards from an ether, I need to think about what are the ether forming reactions I know. Well, I know I can make an ether by an SN2 reaction. I know I can make an ether by an SN1 reaction. And I know I can make an ether by a um, by reaction of an alkene and an alcohol, um, as I showed up here. Alkene, alcohol makes ether. So I know 3 different ways I can make an ether, which means I'll have multiple possible precursors. So maybe first I think of the SN2 route. All right, if I wanted to do an SN2, that's going to mean I need an alkyl halide and my nucleophile would be an alkoxide. Alkoxide meaning RO with a negative charge. So what would these pieces look like? My alkyl halide, the question is, do I want my alkyl halide to be on carbon 4 or on carbon 7? Well, carbon 4 is a primary carbon, carbon 7 is a secondary carbon. So to do a good SN2, I'd like to have a less substituted alkyl halide. So I would put my alkyl halide on carbon 4, which is a primary carbon, and then my alkoxide would be on carbon 7. So 5, 6, 7, and 8, and then my alkoxide would be there. So that's one possible retrosynthetic analysis of this ether. Let's think of another one. I know I can do this via SN1. For SN1, I'm also going to want an alkyl halide, and I'm going to want to use an alcohol as my nucleophile. Okay. In this case, I know for SN1, this is going to be going through a carbocation. So now I know I don't want my alkyl halide to be on the primary carbon because that'll never form a carbocation. So in this case, I want my alkyl halide to be on this secondary carbon. And then my alkyl halide would be, sorry, I flipped these around. Let me move my alkyl halide over here. And then my alcohol would be on carbon 4. Okay, so that would be another possible retrosynthetic analysis. And then my last possibility, I said, would be to react an alkene with an alcohol. So in this case, I know that the RO group, this would be with an acid catalyst again, I know this is going to go through a carbocation. So the carbocation is going to have to be on carbon 7 then. So my alkene would look like this, and my alcohol would have to look like that. So I have 3 possible final steps, and you can choose any one of these and trace it back to the starting material. One of them already includes the starting material, so I mean, this is already essentially a complete synthesis. Notice that this is just another way to draw the starting material. 1, 2, 3, 4, that way. So I could consider that a complete synthesis. I could also turn my starting material into the alcohol here, so I could use all my carbons from the starting material to make the pieces that go into the synthesis. So let's try and write now what a final answer would look like. A final answer for this might look like this. I take my starting material, and I'm going to want to turn it into this alcohol here. The way I would do that, you may remember or may not, would be with hydroboration oxidation to make the OH go to the less substituted carbon. And then I could also take my alcohol and react it with the starting material alkene with an acid catalyst to produce that desired product. So this could be one possible final answer. I could also come up with a final answer that follows the purple pathway if I wanted to. I could also come up with a final answer that follows the red pathway. This is an example where I have lots of different possibilities. But that's our thought process. That's what you want to do when you approach any synthesis problem. So I have another synthesis example on the next page. So I would like you to take a minute, take 5 minutes, take 10 minutes, really dive into that question, and then come back and I will walk through my thought process for this one. But follow these steps. Take a deep breath, identify functional groups, count and number your carbons, and work backwards. Go for it. Okay, great. So hopefully you've already tried this out yourself. Hopefully you identified the functional groups. We start with an alkyl halide. We end with a primary amine. In terms of my carbons, I have 1, 2, 3, 4 in my starting material, 1, 2, 3, 4 in my product. One difference, though, is my functional group was on carbon 4 in the starting material. Now it's on carbon 3. So that's definitely a change I'm going to have to make. I'm going to start by working backwards. So primary amine, I only know one way to make that at this point. So that's good. I know my final step is going to have to be a reaction where I take the corresponding azide and react with H2 and palladium. And I only know one way to make an azide. So even better, I know my azide had to come from an alkyl halide or a tosylate, I suppose, something with a leaving group. Now, I'm drawing these with wedges and dashes, but notice in the product it has this plus minus sign. That means that I get a racemic mixture, which essentially means I could ignore that stereochemistry because I'm going to get both the wedge and the dash. So I'm leaving it in out of habit, but if you left it out, that's okay. So this could have come from an alkyl halide. And I might say to myself, well, I started with an alkyl halide. The problem is this is not the same alkyl halide. So now I have to think about how I could get the functional group, the alkyl halide, from carbon 4 to carbon 3. Because in the starting material it's on carbon 4, now it's on carbon 3. Well, this isn't that hard a problem. I know that I can turn an alkyl halide into an alkene, and then I know I can turn an alkene back into an alkyl halide. But the key is when I make the alkene, now there are 2 carbons in that functional group, and one is more substituted, one is less substituted. I can probably make this change. So this could have come from an alkene that looks like this, and I could make that alkene via an E2 elimination from my starting material. All right, so now it's time to write my final answer. I take my starting material. I want to do an E2 reaction. It's a primary halide, so I'm going to need to use a big bulky base. So I'm going to use tert-butoxide as my big bulky base to turn that into an alkene. Then I'm going to use HBr to turn that into an alkyl halide. I'm going to then react that alkyl halide with sodium azide. And then I'm going to use H2 and palladium to make that primary amine as my product. So there is my whole sequence. If I wanted to in the final answer, I could have probably listed those last 2 steps over the same arrow and just said step 1 and step 2. But it's kind of up to you. In general, I like to write things out with all the intermediates along the way so I can make my reasoning clear. So there's a couple examples. You will get more practice on the skill builder. Definitely let me know what questions you have.